This week we are covering lecture about sinusoidal steady state, mostly about AC power. Recalling the last lecture, we learned about phasors, and phasors were representations of sinusoidal signal. So when you have a sinusoidal signal, you take its amplitudes and you take its phase. So basically, you write the real part of it. The representation of cosine is the real part of an Euler representation. So you take magnitude and the phase, and that becomes your phasor. Okay, so this phasor carries the Vm and the phase inside of it. And if you want to take a reverse phasor, basically reverse transform, then you multiply it with the carrier and then take the real part of it, and it becomes a cosine. Okay, and if you want to show it in a polar form, there is the magnitude and there is the angle. And you can always draw a circle around it. I'm really bad at this. This is the origin, right? And this is also Vm, and this is also Vm. And if you want to write it in rectangular form, you take the cosine, it becomes real part, Vm cosine, and you take the sine, it becomes Vm sine. So that's the imaginary part, and this is the real part. And that's how you can basically switch between the polar form and rectangular form. Phasor transformation, that's what I already taught. You take a time domain, you take the transform, this becomes your phasor in frequency domain. If you want to take the inverse transform, as I mentioned, you take the real, you multiply it with the exponential j omega t, which we call it carrier. Then you take the real part of it, and then that's called basically reverse phasor or inverse phasor, and that gives you back to your time domain signal. Okay. This is I explained. We did some examples, and then we explained the impedance. The impedance is just similar to a resistance. We now deal with the complex numbers. So the division of phasors, voltage phasor divided by current phasor, is impedance. And we looked at the impedance for different terms. Okay, don't forget, impedance is not a phasor though. Okay, so you can write it like a phasor, but it's not a sinusoidal signal. Okay, it cannot be transformed to a sinusoidal function. So we looked at the impedance of a resistor, inductor, and capacitor. For the resistor, it's quite simple. We write the current, the magnitude, a phase. When it multiplied with a resistor, the only thing changes is the voltage, which we call it Vm. Phase doesn't change because the impedance of a real resistance is real, right? And we write the phasors of the currents, Im, and the phase, and we write the voltage on the resistor, Vm, phase. So division of voltage divided by current, it gives you just the real part, the resistance part. So it is not a complex, it's a real number. But for inductor, that's not the case. Why it's not the case? Because when we similarly write the current for the inductor, same current, magnitude on the phase. Well, now the definition for the inductor, the characteristic equation, L times derivative of the current gives you voltage on the inductor. And taking the derivative of this current, the derivative of a cosine is sine minus sine. Right, there's a minus sign here, and the omega comes from, so the magnitude becomes minus L omega Im, right? So L omega Im becomes the magnitude, and the sign, you can, there's a minus sign. So because of the minus, we have a pi in the phase when we're changing back to the cosine. And because of the sine to cosine, we have a minus pi over 2. Basically, sine omega t is cosine omega t minus pi over 2. So due to the minus pi comes, due to the sine, pi over 2 comes. So if we write minus sign as a cosine, we'll have a pi over 2 here. It's important you remember these things. So basically, minus sine equals to cosine, okay? Plus same phase plus pi over 2. And rewriting this voltage as the magnitude and as the phase. Now we have the current phasor, we have the voltage phasor, right? And dividing voltage phasor to the current phasor, the angles cancel. So we have pi over 2 with dividing them. The Ims cancel. So as you can see, we have omega L and we have pi over 2 as the angle, which is J, right? Because why was pi over 2 is the J? Because pi over 2 is 90 degrees, right? So we are at this point, and this point is 1, but because it's imaginary axis, it is j. This point is minus j, this point is minus 1, this point is 1 on a one circle. Phasor'ı cosine üzerinden yapıyoruz. Dolayısıyla sana sine üzerinden verilse direkt onu cosine'e çevir. When we were looking at the impedance, it's the voltage here and this is the current here. And voltage phasor divided by current phasor, it gives you j omega L. And this is the impedance of the inductor. So it's a complex number and there is no real part of it. So the impedance of an inductor is j omega L. And if I ask you, hey, can you draw the voltage and the current on the inductor? Well, this is the current and this is the voltage in time domain. And as you can see, in time domain, there is this extra pi over 2. So if we compare cos and cos blah blah plus pi over 2, well, this pi over 2 makes your voltage leads, because the reason the voltage leads is, I usually look at them at 0 time. So if I give this omega t plus phi 0, here this omega t plus phi will be also 0, and cos pi over 2 is what? It is sin pi over 2 is 1, cos pi over 2 is 0. So cos 0 is 1, and cos 0 is 1, and cos pi over 2 is cos 0 is 1, cos pi over 2 is 0. And this shows you when voltage is at 0, the current is at 1. So basically, I'm just giving an example because this is not 0, so that's not how it is. So if we redraw this, for instance, like that, this is the current and this would be the voltage. So as you can see, this voltage and current have 90-degree phase, and that 90-degree phase, which corresponds to T over 4, and as you can see, voltage comes before the current, and that's why they call it voltage leads the current. And there is this thing called power factor, which you'll learn in this lecture, and that kind of is important. What is what, which one is leading, which one is lagging. And for the capacitor, it's quite similar representation how we show things. We again, instead of writing the current, we write the voltage, because this is the characteristic equation of the cap. So cap capacitance times voltage derivative is current. So taking that derivative, Vt, dV over dt, the derivative of a cosine is minus sine, omega comes front, this becomes voltage. So switching sine to the cosine, we basically do the same thing, minus here. Due to the sine cosine conversion, there is a minus pi over 2 as well. So you get the pi over 2 here, but this time we switched. Instead of starting the current for the volt cap, we started with the volt, right? Because it's easier to take the derivative of the voltage here. So this is the current, this is the voltage, and writing their phasors, we have this, and dividing voltage phasor to the current phasor, VMs cancel, we have omega c at the bottom, and also pi over 2 at the bottom, right? Because we are dividing V over I, and the pi over 2 at the bottom is J. So this is the impedance of the cap. You can also write this as minus J over omega c as well, right? J comes to the numerator instead of the denominator. It's the same thing. So yeah, the important thing to remember from this slide, impedance of the cap is 1 over j omega c, and this time voltage lags. Why voltage lags? Because the phasor of the voltage is this one, theta, and phasor of the current is theta plus pi over 2. So as you can see, this is phi over pi over 2. So that's why current comes front with 90-degree phase. So voltage, this one, lags the blue current. Okay. All right. So the use of phasors in the RL circuits, for instance, for this circuit, what we do to find the current, this is the voltage, which is Vm cos pi. Sorry, 1 second. All right. So this is the source, which you can write it as well as Vm cos omega t plus phi. So, and this is the phasor representation. Dividing this voltage by the total impedance, which is R plus j omega L, you can find the currents. So Vm divided by magnitude of the denominator is this one. And the phase of this current is, because phase here is 0, and the phase of this denominator is tangent omega L divided by R. So 0 minus that will give you tangent minus 1. So basically, how can we find the phase of this? You can simply write this as, hey, this is R. I'm sorry, this is omega L because it's the imaginary part. This is the R. So it's a triangle, and we are trying to find this phase. And the phase is tangent 1 omega L over R, right? And because this is the phase, but this is at the denominator, we have to put the minus sign, okay? Because this is at the denominator, the phase 0. So this goes above as minus, right? Because we're talking about phases. So that's why this is the phase, that's why there's a minus sign here. Did you guys understand this part?
Yes, sir.
Okay, perfect. Similarly for the, also we show this in the polar coordinates, right? So we say that, hey, the voltage on the resistor is, because this is the angle, as you can see, it's a minus phase. So minus phase times resistance, it will be minus voltage phase. So we just can come up with a vector. This is the voltage R, and this is j omega L, but there's a phase for the current. So it won't be 90 degree, but smaller than 90 degree. We can draw a voltage, and some of them will be the total source, right? So you can basically do a KVL on the polar coordinates. VR plus VL will give you the source, right? This is like a proof, but I might give you in the final this one, and from this I might want you to draw the circuits, okay? And that's why you need to understand this vectoral diagram quite well. So in RC circuits, similar logic, but instead of j omega L, now you will do the 1 over j omega C for the capacitor. Now this was where we were left. The sinusoids are important because most of the data, like the pilot data especially, is in sinusoids. So the logic, the reason why the sinusoids are used as pilots, basically test signals, is because it's easy to analyze. When you have an input, which is a sinusoid, the output will be also a sinusoid, whatever the output is, a voltage on anything. And it will be also a sinusoid with a different amplitude and the phase shift, okay? And that's called linear system. It's linear time invariant circuit. So whatever input sinusoid is, output will be another sinusoid with a phase shift and different amplitudes, okay? And that's called frequency response. Output versus input. So V out divided by V in. So, you learn Fourier series, and similar to Fourier series, we will characterize this input-output response with Laplace in this class, in the next 2 lectures. So, for instance, all right, probably I'll teach this later. Oh, it's good to teach. Okay, so for instance, this is a low pass filter, and low pass filter means anything that has a low frequency. So this is x-axis is frequency. So low frequencies pass, and this, let's say this is the response, V out over V in. Any low frequencies will pass, and high frequencies will not. Low frequencies will pass, high frequencies will start to drop, like not pass. Well, does it make sense? Well, let's give it a try. The impedance of this cap is, what was it?
J omega C.
1 over j omega C. So at low frequency, what is the impedance? At, let's say, 0, when omega is 0.
It's infinity.
Infinity.
Right, the impedance is infinity. 2 pi f 0 1 over 0 is infinity. So this is open circuit. Let's cut it here. So if Vs is here, what is this voltage? It's Vs, right? There is no current here. It's open here. It's open here. So whatever Vs will show up here. So as you can see, if we divide V out versus Vs, output over input is 1. But then when we start to increase the frequency, this cap starts to, the impedance of the cap starts to drop. So if the omega is infinite, like very high, at let's say some point here, if the omega is infinite, what would be the cap impedance?
0.
This time is 0. So as you can see, this time this is
Shorted.
ground, shorted to the ground. So that means this one is 0. So output divided by input is 0. Okay, so we are basically here. Let's say maybe I should have drawn it like this. Anyways, so the point is the low frequencies pass, high frequencies don't. That's why it's called low pass filter. And if you analyze the circuit, how to analyze this, you write R and you write 1 over j omega c. And instead of that j omega, we use S, Laplace transform. And this is time domain, okay? And instead of doing this in time domain, as you can see here, which is quite complex, hard way, right? You can do it in the AC domain. And AC domain is just the way I taught you. You write the impedances. And when you write the impedances, it's RC circuits. You find the magnitudes, V out over Vs. And as you can see, as we increase the omega, this one starts to drop, V out over Vs, okay? And if we draw them, actually I draw quite bad. You know, I draw like that because I draw in logarithmic scale. So if we draw it in linear scale, you'll see that it starts at 1 and goes towards 0, the amplitude response. And this is also the phase response, okay? Phase response means V out over Vs. You take the phase of it. Okay. Why the phase is important? Well, every linear system needs to be also analyzed in terms of phase because we need to check if it is prone to oscillation and if it works fine. So we will teach you oscillation in feedback systems much more in details, but mostly you need to care about this amplitude response at this time, okay? So, well, if you draw this in dB, just like the way I did, so if you draw this curve instead of decimal, if you draw it in dB, this is what you get, right? So the x-axis is logarithmic, and you take the decibel. So you'll, instead of a sharp drop, you will see a much lower drop because here the frequencies are still small. Basically, you are drawing this in the logarithmic scale. Anyway, also you need to know how to convert a decimal to a dB. You take 20 log that number. So if the 1 is what? 0 dB, right? 20 log 0 is 20 log 0 is minus infinity. So that's how you do it. You give omega some numbers, and then from that you can put it in the equation and write the gain. All right, so we went through this, You know, these are just for your, again, we already studied this complex exponential, how you can write them, complex numbers, LTI. So now we go to the power calculation. We need to calculate how much power these systems are actually dissipating. Well, AC is sinusoidal, alternating current. DC is like DC, direct current. The key points with this power calculations will be, you need to understand what is the average power, and you need to understand what's the reactive power. Or in some other terms, you need to understand what is the phase component of the sinusoidal power and what is the quadrature component. And you will learn it's something called power factor, and how we can, if we have time, we'll also check how we can do the power factor correction, and which you can benefit this from the energy systems class. All right, so as you know, the power is voltage times current. So we find the voltage of between two nodes, whatever the current getting in, we multiply voltage with the current. And if it's a voltage providing currents to the outside, well, then that will be basically minus sign, because the voltage source doesn't absorb power, but it delivers power, right? So that's called instantaneous power, that voltage times current. There is this important slide here. This is the voltage and this is the current. And as you can see, the magnitude is of course different, and the phase is of course is different, because we assume there might be a phase difference. This is the current, and we don't know the impedance. It might be R plus J omega L, right? And resistor and an inductor. And we say this is the voltage on it. So the currents we can write like that, and the voltage we can write like this. And we multiply these two terms, Vm cos omega t plus theta v, and Im cos omega t plus theta I. You can write them in phasor domain, but first I show you how you can do it in time domain. So here, this phase theta v minus theta I, we just write their difference as an angle. And this angle, we can basically rewrite these voltages and currents if you want, because what we care is their difference. And when we write them, when we multiply Vt and It, actually we are multiplying Vm and Im, and also we are multiplying this cos omega t plus that and cos omega t. I mean, we can also do the same thing. It will give you the same answer. This is just explaining that there is this phase difference between them, which is this one. So when we multiply two cosine, we subtract the phases, we add the phases. So omega t plus theta v minus omega t minus theta I will give you, well, omega t becomes 2 omega t plus phases, which is beta. So that will be giving you this side. And when we subtract them, it will give you this side, right? So summing them, 2 omega t plus phase, subtracting them, voltage phase minus current phase. And as you can see here, we have a cosine, a sinusoid function, and we have cos phi. Well, this one is not sinusoid, because this is a constant number, cos 60 degree, cos 45 degree. This is the number. So you can see that a sinusoid or cosine current, cosine voltage, their multiplication gives you a DC term, which we call it constant P average, and also an oscillating term with the oscillation of 2 omega. So if we go to the next slide, for instance, this is the current, which is dashed, and that the other one is the voltage, right? And their average around 0. So basically, this is the current, and the voltage is the blue one. So when we multiply them, you see, instead of having the 0 average, now we have the P average at a DC, right? And the swing becomes 2 times their frequency. Instead of omega t, their swing is right now at 2 omega. So at DC, you see a swing, the one in the red. And if you go to the previous slide, you'll see that makes sense. You have a DC term, like basically an offset, and around that offset, you have a oscillating power. I did it badly. You can decompose this power even in different ways. So as you can see, there was that DC part, and there was this oscillating part. Taking this Vm Im over 2 to outside and putting them in parentheses, so cos phi, and we write this 2 omega t plus phase difference. We basically separate into cos minus sin, and we rewrite that. And now you can actually have this new terms called in phase and quadrature. Why is it in phase and quadrature? Because we put some terms with the cos and we put some terms with the sine together. So as you can see, this Vm over Im2 is at the outside, which is P, this term actually. That is the P, as you can see here. So, and we separate the P and the Q into two parts, basically from here. And P is, this is called average power. And this Q, quadrature, because it's the term in front of the sign, and that's called reactive power. So the reason this is called this P called in phase and this Q called quadrature, because cos and sin, actually they are quadrature signals. Can anybody tell me why they are quadrature signals? Well, what's the definition of quadrature?
No, I don't know.
So anything that is their multiplication is their phase is 90 degrees. Basically, they are independent of each other. So you cannot write cos in terms of sign. I mean, you can, but the way that I'm meaning is like any vectors A times B, if they are perpendicular to each other, what is the result? They are perpendicular to each other. So J times I. Yeah, so cross product. So what is this times this? So you studied calculus, right? So this is called I, this is called J, this was K. I cross J. J cross I minus K, right? So similarly, if we do a dot product, I dot J, what's the result? 0. The quadratures, these are quadratures. If I draw two vectors or even three vectors, I, J, K, these are all quadratures because they have 90-degree phases in the 3D domain. So any quadrature signal, their dot product will give 0. Similarly, cos omega t and sin omega t, what are their phase differences? They are pi over 2. You can write sine as cos omega t minus pi over 2. Okay, and as you can see, their phase difference is pi over 2. So of course there's the carrier aj omega t, but just like I explained in the phasors, we are caring about the phase. So cos omega t, sin omega t, we can think it like I and j. Okay, so and these are independent. Any vector, we write it as, hey, this is 4i plus 3j, right? So these are independent representations. They are independent vectors. That's why, because we can write a signal as cos and sine, but we can basically write it just like the way I wrote here. We can write 4 cosine omega t plus 3 sine omega t. So that's why the parts in front of sine, it's a quadrature signal, quadrature power, Q, and parts related to cosine, it's in phase. You might say there is a 1 here, and I'll tell you why we keep the 1 there. But this is the most important part. So when I ask you what is the average power of this circuit or of this impedance, let's say it's a black box, which there is R and L inside. So you'll take the phasor representation of the current, you write its magnitude, you'll find the voltage, you multiply it, and their phase differences, cos theta, is their phase difference, right? If you go to the previous slide, the I will have a phase, the current, the voltage will have a phase, and their difference, voltage phase minus current phase, will be this. So, and you multiply that with cos, that gives you average power. You multiply it with sine, that gives you reactive power. So from this question, if we have no R, just L, what is the average power of this black box, of that orange box? Well, let's think together. L is j omega L, right? L has an impedance j omega L. So let's say the phasor of this current 0. What would be the phasor of the voltage? The phase of the voltage, pi over 2, 90 degrees. So now we know this one. Vm times Im, their phase difference is 90 minus 0. So what is this angle? Pi over 2. What is cos pi over 2? 0. And as you can see, average power of an inductor is 0, but the reactive power is Vm times Im over 2. Okay, and it makes sense because the inductor is purely reactive. It doesn't have any resistor components. So what if we have a cap? What would be this phase here? Minus pi over 2. So what is cos minus 90?
Again, 0.
Again 0, right? And what is sin minus 90?
-1.
Minus 1. So basically we put up minus here. So as you can see, reactive power of the cap is again now this term with the minus, and average power is 0. It makes sense because cap impedance is purely reactive, right? But instead, if we add some R, now this phase won't be 90 anymore or minus 90 anymore, because now this is a real and imaginary parts inside the box. So both you'll see average power and reactive power. Okay, basically average power will be the power due to the resistance, and the reactive power will be the power due to the inductance or capacitance. So this is some kind of, you can think it like absorbed power on the resistance, and you can think it's this a power, reactive power that is stored in the inductor. When you conduct currents, the power on this resistance, it is transferred as heat. We lose that power, okay? Like your kettle, you plug it, there is a resistor inside, the current flows, AC current flows, and this resistor heats, right? So, and that's average power actually. But the power on this inductor, this current goes through the inductor, it creates a flux. So you use a thumb rule, the current goes to the right, your four fingers, so you have a flux. And this flux is always in the environment. It doesn't get lost. Okay? There are Faraday's law, Lorentz law, you're probably taking an EM class. So just learn EM very well. Electromagnetics is really important. So that is reactive power. That's the energy that is stored on this inductor. This is the in phase. This is the quadrature. The reason it's saying with in phase, as you can see here, the blue starts from here, right? And the overall signal, overall power, which is the red one, it also starts from here. So as you can see, they're in phase. They start with the same phase. One is this, the other one might be maybe even this, doesn't matter, but they start in phase. But the other one, it starts not in phase, right? It starts somewhere else. So that's why we say it in phase. And the quadrature, well, we have 90-degree phase because this is cos, this is sine. Okay, so I already explained these things, average power, but I can explain again so you will not forget. Okay, so as I mentioned, the average power is the power transformed from electrical energy to some other energy, like just like in the resistor, electric energy converts to heat, right? Or it might be something else. The electrical energy turns to some other energy. So, and that is the definition of average power. And whatever the instantaneous power is, PT is VT times IT, and whatever the mean of this power is your average power. So when you multiply these things, you might have 5, cosine, sine, blah, blah. And when you take the average of this, you'll have eventually DC component. Here it is probably 5, okay? So, and that is basically your average power. That's average of that instantaneous power. So as you remember from the previous slides, the average of this is in phase with the current. That's why, we call it in phase. And you already know this, the circuit dissipates electrical energy if the power is bigger than 0. So what is reactive power? Well, the example I give you, if it's inductance or capacitance, the power doesn't get lost. The power is exchanged or stored. In an inductor, it becomes a magnetic field. In a cap, it becomes the charge. And so, because the cap stores the charge, so it turns as an electric field, okay? And as again, we went through the math, the magnitude of the sine term becomes, because it's in quadrature, 90-degree in phase with the cos term, that's the reactive power. And again, reactive power cannot do the work. It is just exchanging power. If it is a resistor, the phase difference is 0. Because the phase difference is 0, the reactive power is 0, okay? As you can see, we only have the in phase component, so average power. Reactive power is 0. For inductor, as I mentioned, this time average power is 0, but you have the reactive power. And for the cap, same thing, you have the reactive power only. So now there is this thing called power factor. So the power factor is cosine of that angle. Which angle? The angle between voltage and the current. Okay. So similarly, we have a load. Let's say it's just inductors, one inductor inside. So what will be the power factor?
90 degrees.
Cos 90 will be 0. So power factor for a inductive load will be 0. Power factor for a capacitive load will be minus, right? So basically, simply, you take the relative phase between voltage and current. This might be 45 degrees, for instance, if we have a resistance here. So that phase basically tells you how inductive, how capacitive, or how resistive is your load, right? We have only inductive loads. It was 90 degrees. We added some resistors. It was 45 degrees. If we add a lot of resistors, this becomes very small. Well, it will be 0 degree, right? Because it's only resistor. Well, if we add a lot of cap, now it will go to minus 90 degrees if the cap dominates, right? So between 90 degree minus 90 degree, that phase will tell you if your circuit is inductive or if your circuit is capacitive. Power'ın iki tane term'i var. Bir tanesi bu, average power. Siz hep average power öğrendiniz. Bu inductor'ları, kapasitansları bilmediğiniz bu derse kadar. Niye? Çünkü hep resistive diye düşünüyorsunuz, değil mi? Ama bir load aslında resistive değildir. Bir load'un içinde inductor da vardır, kapasitör de vardır. Bu üçünün kombinasyonudur genel olarak. Dolayısıyla artık devreye reactive power diye bir şey giriyor. Bir harcanan güç, geri alamayacağınız enerji average power. Ama depolanan power reactive power'dır. Yani sizin demin anlattığım gibi bir load'unuz var. Burada mesela bu bir transformer olabilir, bir enerji devresi olabilir. O zaman bu daha çok inductive olacak. O zaman onun daha sonra derste, enerji dersinde anlatır hocanız. Mesela böyle bir devrede sadece inductive ise average power yoktur. Neden? Çünkü bir tane base alırsınız. Base derken mesela current'ın fazını 0 verirsiniz. O zaman voltajın fazı ne olacak? Demin anlattığım gibi 0 fazı current J omega L ile çarpıyorsunuz. O zaman açı 90 oluyor, değil mi? Akım çarpı rezistans. Dolayısıyla bu ikisinin voltaj fazıyla current fazı arasındaki açı 90. Cos 90 0 dedik. Dolayısıyla bir inductive ise veya capacitive ise bu sizin zaten adı üstünde reactive olduğunuzu gösteriyor load'unuzun. Okay? Hiçbir average power yoksa sizin load'unuz tamamen hiçbir resistance içermiyor. Tamamen reactive, inductor or capacitor. Ama araya bir iki rezistans koyarsanız, şurada bir rezistans koyalım şöyle. O zaman bu 90'ı 45'e, hatta deli gibi rezistans koyarsan ne olur? Açı tekrar sıfıra gelir. O zaman da reactive power'ı sıfırlarsın. Bu demek değildir ki içeride hiç inductance yok. İçeride belki inductance var ama çok küçük. Yani rezistans 1000 olsun, inductance da 1C olsun, değil mi? O zaman şu açı, şu domine ettiği için çok küçülecek. 0.1 olacak mesela. Neredeyse çok resistive olacak. Yani bu açıya bakarak
bize hani bu average power mı, reactive power mı olduğu depolandığını mı yoksa daha çok harcandığını mı söylüyor aslında?
Evet, aynen öyle. Yani sadece demin anlattığım power factor'a bakarak şuradaki aslında bu size bunu söylüyor. Power factor şurası aralarındaki açı olduğu için power factor burası daha çok average power'ı gösteriyor. P average. Burası da daha çok sin phi olduğu için P reactive'i gösteriyor. Şurası power factor. Cos phi. Dolayısıyla buradan görebilirsiniz load'unuzun özelliğini. Bir de işte şu RF'de reactive factor diyorlar. Ya, power factor, reactive factor zaten birbiriyle alakalı. Yani power factor 0 ise ne olacak? Reactive factor doğal olarak 1 olacak veya vice versa. Okay. Burada power factor also lagging term'de kullanıyoruz. Power factor lagging demek şuradaki açının sıfırdan büyük olması demek. Yani işte açı 0 olunca resistive oluyordu. Neyse mesela sıfırdan 90'a doğru çıktıkça resistor'dan inductive'e doğru çıkıyorsunuz, değil mi? Dolayısıyla inductive bir load ne demek? Inductive load'da voltage 90 derece. Burada lagging PF demesinin nedeni, bunu şöyle düşünebilirsiniz lagging ve leading olayını. Mesela bir cos omega t olsun, bir de cos omega t plus 90 derece olsun. Şu ikisinin aynı yere gelmesi için şu t'nin eksi olması lazım değil mi? Yani eksi derken mesela şuna bir A diyeyim, constant. Bunun hepsinin A olması için bu t aslına bakarsanız bir eksi değerde. Yani bu tarafta. Dolayısıyla önce geliyor. Yani time şuradaki time'a göre daha önce. Okay? Ben hep böyle düşünüyorum. Dolayısıyla daha önce ise bu lead'dir. Daha önce geliyordur. Okay? Mesela bu voltage'sa ki hani şöyle yapmıştık. Yani kısacası şu faz farkı o sinyalin artı olduğu için daha şuradaki t'yi sanki eksiye götürüyormuş gibi düşünebilirsin. Okay? Şuradaki t buraya göre daha ekside. Daha önce geliyor. Veya hangisinin maksimuma ulaştığı şuradaki voltajdan daha önce maksimuma ulaşıyor. Burada power için bilmeniz gereken 3-4 tane önemli şey var. So there is this thing called RMS power. So RMS means root mean square. So you take the square, then you take the mean. See, this is how you take the mean. You take the integral of it between 0 and t, a period, and you divide it by the period. The RMS value of a sinusoidal function. RMS value'su nedir? Şudur. Neden budur? Bunu nereden geldiğini şu şekilde bilebilirsiniz. Amplitude'un square root 2 ile bölümü sinusoidal bir fonksiyonun RMS'idir. Bu RMS ne demek hocam? Niye RMS kullanıyoruz? Aslında RMS şu demek. Mesela işte gridden 120 volt sinyal alıyorsunuz. Aslında bütün işi yapan bu sinyal 120 voltluk sinyal değil. Aslında işi yapan sinyal 120 bölü kök 2. Yani kaç ediyor işte? Kök 2 ile çarpsak 60 kök 2 olan yer yapıyor. Bu ne demek? Yani aslında şuradaki 120 voltluk salınım şuraya vurduğumuz zaman RMS'e 60 kök 2'ye varıyor. Aslında siz iki tane sinusoidal sinyali çarptığınız zaman ne elde ediyorsunuz? Sin square elde ediyorsunuz. Değil mi? Power aslında sin square. Dolayısıyla eğer bu sin square bunun daha sonra integralini alıyorsunuz, mean'ini alıyorsunuz. Bunu elde ediyorsunuz. Dolayısıyla burada yani bu root mean square size şunu söylüyor. Mesela bir şöyle gene çizeyim. Bir black box'ımız var. Burada IM var. Burada da VM var. Mesela IM ile VM'i buldunuz. Power'ı average power'ı yazarken nasıl yazıyorduk? VM çarpı IM bölü 2 diyorduk. Değil mi? Aslında artık böyle dememize gerek yok. Aslında artık VRMS çarpı IRMS diyebiliriz. Niye? Çünkü şu 2'yi aslında kök 2 diye yazabilirsiniz. Okay? Dolayısıyla burası sizin voltage RMS sinyaliniz. Burası da current RMS sinyaliniz. Dolayısıyla gördüğünüz gibi RMS sinyalleri birbiriyle çarptığınız zaman aslında gerçek power alıyorsunuz. Yani şuradaki 2 aslında sizin tekrar matematiğe bakarsanız şuradaki cos square'in ayırıp bunu 1 artı cos şeklinde yazmanız. Cos 2'nin integrali demin görmüştük. Herhangi bir cos'un integrali sıfırdır. Dolayısıyla buradan bir power gelmeyecek. Dolayısıyla şu cos square'den gelen power aslında şuradaki average'den yani DC'den gelen power. Okay? Bir cos square sinyalini veya sin square'da olmuyordur. Cos square'da 1 artı cos 2 omega t diye yazıyoruz değil mi? Dolayısıyla power'ı getiren yer burası. Burası değil. Yani bir cos square sinyali iki tane farklı terime bölünüyor. 1 artı cos 2 omega oluyor. Şu 1 artı dediğim yer aslında VM square. VM'i dışarı aldık. Dolayısıyla power'ı getiren yer aslında DC olan yer. Çünkü herhangi bir sinusoidal sinyalin cos veya sin integralini aldığımız zaman 0 olur. Böyle bir sinyalin RMS voltajı nedir dediğimiz zaman direkt VM'i alacaksınız. Kök 2'ye böleceksiniz. Cos olmasın bu bir triangular signal olsun. Mesela şöyle olması yerine mesela şöyle bir sinyal olsun. Okay. Root mean square değil mi? Karesini aldığınızda eksi kısım gider. Aslında siz bunun burası hala VM mesela. Bunun average'ini buluyorsunuz. VM over square root 2. Bu artık bir sinyal average'ı da bu. Ama dediğim gibi bir triangle olsa şöyle mesela. Bunun square'ini alınca bu triangle yukarı çıkacak. Dolayısıyla triangle'ın average'ı VM over square root 2 değil. Yani şu mathematical fonksiyon yaparak bulabilir. Sinyalin square'ini alacaksınız. Sonra mean'ini alacaksınız. Mean'i almak demek bir periyotta integralini alıp o periyoda bölmek. Sonra da root'unu alacaksınız. Okay? Bu size aslında gerçekten o sinyalin effective value'sunu veriyor. Yani şuradaki amplitude'un gerçekten efektif olarak nasıl işlendiğini görüyor. Bunu biraz daha
kısacası özetle the most important things you guys learned in this class, power is actually an average power and a reactive power. And this is the formula for the average power. This is the formula for the reactive power. And the most important thing is what is the phase difference between the voltage and the current phasors. Okay, these are the amplitude, right? But they have phases. So the difference of those phases is this part. And from this part, you can understand if it is an inductive, if it is resistive, or if it is capacitive load. So if you have a lot of cap but a little resistance, this is a capacitive load. Why? Because minus j over omega c is much bigger than resistive part R, then that is capacitive. Or if it is inductive, that means j omega L is much bigger than R. Okay, so and this makes it inductive. If you have some inductor and capacitor, and this minus j and j, well, they might cancel each other at a certain frequency, which is called resonance frequency, right? So let's say this is 30j and this is minus 30j, and then that means they are in series, they cancel each other, and you'll only see R. So then your circuit becomes resistive, even though you have caps and inductors, okay? So it doesn't mean that having an inductor or cap necessarily makes it inductive. You need to look at the impedance right here and check what is the real part, what is the imaginary part, right? And then you can determine if it is inductive. Is the imaginary part, which is J, much bigger than R, then that is inductive. Minus J is much bigger than R, then that's capacitive. So basically you need to look at the equivalent impedance. So then that will tell you how much average power and how much reactive power your circuits will have from these formulas. Meaning of RMS is a sinusoidal voltage source of RMS value VRMS and a DC voltage source of constant Vs deliver the same average power to a load resistance R if RMS is Vs. Dediğim gibi aslında bir AC sinyalin RMS'inin mantığı şu. Yani AC sinyalin yaptığı iş aslında VRMS'te gizli. Siz bir DC sinyal koysanız, Vs deseniz, okay, ve buraya bir rezistans koysanız, bu rezistansa AC power'ı verebilmeniz için, ya AC bir sinyalle power verebilmeniz için vereceğiniz voltaj ne olmalı? VM ne olmalı? Söyleyebilecek var mı? Bir sinusoidal sinyal için. Şurada aynı power'ı elde etmek istiyoruz. RMS'in formülü neydi? RMS'in formülü şuydu değil mi? Sinusoidal amplitude divided by square root 2. Bir sinusoidal sinyalin amplitude'unu square root 2'ya böldüğümüz zaman o size o sinusoidal sinyalin RMS'ini veriyor. Değil mi? Buradan yola çıkarsak demin çizdiğimde o sinusoidal sinyalin voltajının ne olmasını isteriz? Square root 2 times Vs olmasını isteriz ki RMS'e Vs olsun. Okay? Ya RMS dediğimiz gibi aslında işi yapan voltaj. Neden? Çünkü root mean square. Burada bir soru var. Demiş ki lambanın ratingi 100 watt ve 120 volt. Rezistansını bulun demiş. Buradan VRMS square bölü pi ile bulabilirsiniz. Neden? Çünkü power aslında voltage bölü resistance, değil mi? Ama artık sinusoidal'dan bahsettiğimiz için V square over R değil de VRMS square over R. Çünkü eskiden V square over R diyorduk ama bu DC'di. Şimdi artık o DC'nin görevini RMS yapıyor. Çünkü AC'den bahsediyoruz. Dolayısıyla VRMS square R size pi veriyor. R'ı bulmak için de yer değiştiririz. R'ı pi yaparız, pi'yi R yaparız. Bunu da bu şekilde yazarız. R 144 çıkmış. Burada önemli olan yer şurası. RMS 120 volt dediği için RMS'e 100 watt koyuyoruz. Şuraya da 120 koyuyoruz. RMS current. O zaman da direkt RMS voltajı rezistansa bölür. Yani RMS voltaj 120 idi. Rezistans 144'tü. 120 bölü 144 0.83. Peak current nedir dersen RMS'i kök 2 ile çarpacağız. Bu kompleks ve average power'ın aslında represent edebilirsiniz. Şurası VRMS çarpı IRMS veya VM çarpı IM bölü 2. Q'su da tabii şu cosine. Şurası aynısı sine. Şurada aralarındaki voltajla akımın aralarındaki faz fark. Dolayısıyla average power cosine yani real part diye düşünebilirsiniz. Reactive power da şurası imaginary part. Çünkü C var başında ya. Dolayısıyla onu da C olduğu için aslında şöyle şuraya koyabilirsiniz. Toplamları toplam power verir. Toplam power'a da apparent power deniyor. Absolute olarak. Average power'ın birimi watt. Zaten bunu biliyorsunuz. Çünkü resistive. Reactive power'ın volt, amp, reactive. Yani var. Bu da yeni bir şey. Okey. Bu soruları sizin çözmeniz için bırakıyorum. Mesela power factor lagging demiş. Buradan aradaki açıyı bulacaksınız. Demek ki cos phi 0.8. O zaman açı kaçtır? Buradan bu load'un karakteristiğini de bulmuş oldum. RMS voltajı vermiş. Üzerindeki power'ı vermiş. Ama average power'ı vermiş. Bir reactive power da var. Çünkü 0.8. 0 olsa tamamen induktif. Sadece resistive. Aynen. 90 derece olursa
Sadece L'dim.
eksi 90 derece olursa okay. Dolayısıyla 0.8 olması için hem bakıyoruz 1'e yakın. Dolayısıyla biraz daha çok resistive diyebiliriz. Ama bir şeyler aşağı çekiyor. Ne aşağı çekiyor? Mesela cos 10 olsun. Dolayısıyla biraz induktif var demek ki. 90 dereceye doğru gidiyor. Bir de şunu anlatayım. Maximum power. Maximum power transfer'de olay hatırlıyor musunuz? Neydi?
İç dirence eşit olmak zorunda.
Aynen öyle. Bir voltage var. Voltage bir aresi var. Dolayısıyla bu load'un maksimum power gelmesi için RS olması gerekiyor. Şimdi artık kompleks impedanslara ekledik. Bu iç direnç RS artı X olsun. Yani imaginary bir şey olsun. Buraya maksimum power'ı verebilmemiz için RS duracak ama eksi, şuraya JX diyelim. Kafamız karışmasın. Eksi JX olacak. Kısacası load'unuz artık direnç olarak aynı ama kompleks tarafına minus koyacaksınız. Buna da conjugate deniyor. Yani artık impedans kullanıyoruz. Dolayısıyla bir source'unuz var. Burada bir impedans var. Bu load'unuzun maksimum power gelmesi için impedansı Z conjugate. Yani bu Z R artı JX'e bu Z conjugate demek. Kompleks tarafa eksi koyuyorsunuz. Yani işaretini değiştiriyorsunuz. Burada bir resistor var. Burada bir inductor var. Siz buraya power transfer etmek istiyorsunuz. Tamam. Dolayısıyla ne yaparsınız? Buraya gene aynı rezistansı koyarsınız. Şu inductor'ı bir şekilde oradan yok etmek isteyeceksiniz. Kapasitans koyarsınız. Dolayısıyla bu inductance'la kapasitans aslında birbirini götürür. Şuradaki akımı maximize etmiş olursunuz. Şu x ekseninin mesela şey olduğunu düşünün, x olduğunu düşünün, x ekseni. Dolayısıyla siz ancak bu current'ı maximize ettiğiniz yer şu inductor'ı yok ettiğiniz impedansta olur. Okay? Aslında rezonansla aynı şey. Seri RLC gibi düşünebilirsiniz bunu. Dolayısıyla o X'te veya o frekansta buradaki current maximize oluyor. Current maximize olursa average power neydi? I square times R, değil mi? Current square çarpı resistance. Yani çünkü real part'a bakıyoruz average power'da. Şey neydi? Reactive power neresi? Öbür taraf. Okay? Burada proof var. Average power niye ZL, ZT conjugate. Okay? Proof'a bakabilirsiniz. Yani tabii ki derivatif alarak yapıyor. Ne yapıyor? İşte current şuradan demin anlattığımız gibi voltajı toplam rezistansa bölüyor. Sonra bunu maximize etmek isteyeceğiz. Dolayısıyla maximize yaparken matematiksel olarak neye bakmamız lazım? Derivatife sıfır olduğu yere bakmamız lazım. Çizersek mesela power'ı şurayı bulmamız gerekiyor değil mi? Dolayısıyla load'a göre derivatifini aldığı zaman sıfır eşit olduğu yere bakıyor. Bu da size diyor ki benim load'umun ters eksi olması lazım. Load'un conjugate şeyin reactive part'ın. Okay. Varsa sorunuzu alayım yoksa bitirelim.